we have a reaction diffusion equation. So B is some biological variable of interest, and we assume that whatever that constitutes that B has this feature of random movement in space. So as you can see, I'm only writing X, I'm not writing Y, but whatever I'm doing in 1D, you can easily generalize it to 2D as well. Okay. So now this is also a dynamical system, but not just one variable. Now there are variables spread over a continuous space. So what you're really now dealing with is not one variable, but technically infinitely large number of variables. Okay, because you're in a continuous space now. So we have just jumped from 1D model to an infinitely large dimensional model. Okay. So how do we go about analyzing this? Now recall the two concepts we learned. One is that of stability. One is that of fixed point. Other is that of stability. So we can ask the same question. Can I define a fixed point for this? Can I investigate stability for such a fixed point? So can anybody say, can we define a fixed point for this system? The same definition would hold true. So in an equation, in a dynamical system, without this, we define fixed point as something when the system stops changing over time. So B stops changing. So dB by dt was equal to 0, therefore F was equal to 0. So now for the left hand side to be 0 now, how do we? We have to have both sides 0. Basically the entire right hand side to be 0, right? Is that same as just FB is equal to 0? No, so we need one more term to be 0. So how can we achieve that? This requires you to have some intuition about diffusion. So without that, it's really, really hard. So let me give you some intuition about diffusion based on what Sudipta covered yesterday. So basic idea of diffusion, as I mentioned, is the underlying process is random walk. So let's assume this is X and this is B. Initially, let's say there is a large concentration of B at origin. It's like the large number of particles or individuals at t is equal to 0, at x equal to 0. Now, if everybody now starts to move randomly, what happens to this spike of B? It spreads, right? Over time, what you will see is this. What happens if you wait really long enough, infinitely long time? It would just basically uniformly spread. So the basically, what density? I mean, yeah, whatever the individuals get basically roughly uniformly get. So basically what diffusion as a process does is to make things uniform. It spreads things around. Even if you start with the concentration, it makes things uniform. Okay. Now, does it give you some hint how to? So in this equation now, what is this doing? At any point, whenever it sees some inhomogeneities, what does it tries to do? It tries to kill it. So with that intuition, can you guess what could be a fixed point for the system? Remember that when we say a fixed point here, it's not one variable anymore. It's not the value of B. It's value of B at every location. So throughout the entire space, what is this landscape? What is the functional form of B that can actually in space that can make things? So that's very good. Yeah. So basically, this intuition tells that this term will be 0, right? When everything is same. Basically a flat landscape. If the population density is same across the entire landscape, that's when this term will be 0. When will this be 0? that we already know. That's what we call, right? So let's consider all values of B. Let's consider B star such that f of B star is 0. Okay, and let us assume that B of x is equal to B star for all x. Okay, so basically whatever we have a so we call this a non-spatial or a mean field model. So mean field model has some fixed point. If I make the entire landscape at the fixed point of the non-spatial model, every place has B star in this landscape. So every place f of B is 0. And because every place has the same value of B, the diffusion will also be 0. So basically this is called the homogeneous solution. The homogeneous solution of the mean field model, that will be a fixed point for the entire spatial model. Is it clear to everyone? So if you again think of the logistic model as an example, there were two possible equilibrium, fixed points, right? One is 0, other one was k. So what this means is if it was 0 everywhere in space, that would be one fixed point. If it was k everywhere in space, that would be another fixed point. In the alley effect model, it will be 0 everywhere, xc everywhere, or k everywhere. So all of them basically homogeneous values of that fixed point will be the fixed point for the reaction diffusion equation. Is that clear? Okay. So this one can say is a trivial solution, right, in some sense. Now I have basically trivialized this term. It is not really doing anything. I have basically killed this term by making everywhere the same value. But how do we know it is stable? It's a fixed point, right? But how do we know it is stable? That requires some calculation, right? Even there we required some calculation. We knew that if the slope of this, if that was negative, that would be stable, right? So then what is the equivalent measure here? In fact, let us make an assumption. Assume that B star, some B star, not all B star, some B star is mean field stable. Meaning if prime of B star is negative. Okay. So if we did not have the diffusion term, that would have been a stable equilibrium. If this is the case, with diffusion, what will happen? Will it still be stable? Okay, that's the question we would like to now address. Okay. To do this, we will employ the same machinery that Partha did for the other case. I hope the question statement is clear. Okay. So what do? We basically okay. So what we do is that at time t is equal to 0, we assume that we have a B star everywhere in landscape, but we make a small perturbation, but this perturbation could depend on space. So the perturbation sometimes in some places I have increased the population size, in some other places I have reduced the population size. It's not necessarily uniform. Okay. So I have made this perturbation. The question we can now ask is, how does this change? Will this decay? Will this explode? What happens to this? Okay. So let's now plug this to that equation. So what will be dou v by dt? This time will be 0. The left-hand side would be just the rate of change of perturbation. What about the right-hand side? That would be equal to f of B star plus B plus D Is that right? Okay. Let us assume that this perturbation is not too large. It's tiny enough that I can do a Taylor series expansion and keep only a few terms. And then so on. That is this term, and then we have a diffusion term. When the diffusion applies to this, that would be 0. What you have is just okay. So what is this? That is 0. I have already told you this is negative, but this, we can just keep it the way it is. Let's call this lambda exactly the way I was calling, and let us ignore this term. Ignore higher order terms. Okay. So what we now have is that so rate of change of this perturbation that could be in space as well around the homogeneous equilibrium follows this equation. Approximate because I have dropped the higher order terms. Okay. So far, is everyone with me? Okay. So now, what can we say from this? So the rate of change of perturbation is b lambda, like before. Earlier, we didn't have this term. Therefore, from the sign of lambda, I could have just told the stability, right? If lambda was negative, this would then just exponentially decay. If lambda was positive, it would just be exponential growth. But the thing is, I have this extra term now. It means, I have to account for this. Even if b is negative, what will diffusion do? Will it be a positive term that will compensate for the negative values here? What exactly happens? And that's not very clear. Yeah. This is the initial condition. Okay. Let's call this. This is the initial condition, right? And I want to know how this initial condition changes over time. And that is this. So this is not for t is equal to 0. It will be 0. Any questions so far? Okay. So now we can do a simple analysis. Imagine that what we have done is we have set the entire space at the fixed point, one of the fixed points of the mean field model. And then imagine I make a perturbation that is uniformly above. Okay, that means every point has been perturbed by the same amount, the same direction. What would happen to that perturbation? That would also follow this equation. In that equation, this would be, let's say, negative. Let's say lambda is negative. Okay, just locally it's all getting killed. And what is this term? It would be 0 because every place I have made the same perturbation, right? That means a homogeneous perturbation will also decay. That we all agree, right? If lambda is negative, if the lambda is positive, homogeneous perturbation also go. But we want to do something more complicated. What if I make inhomogeneous perturbations? And then I can't be sure, because in some places this will be positive, in some places this will be negative. So now how do we deal with this problem? To do this, you need to know something very fundamental that most of you know by now. So under some conditions, okay, any function can be written as summation of sines and cosines. So all of you know what Fourier analysis is. The basic idea behind Fourier analysis, any function under some, when it follows some nice condition, few basic properties, it can be written as summation of sines and cosines. So we are dealing with a small perturbation. Okay, a smooth, let's say a smooth, it didn't not technically be even smooth perturbation, but let's say our perturbation follows those conditions. Okay, so therefore I can write that write B as summation of various sines and cosines. Okay, that's an assumption I'm going to make, and in fact I'm going to make one more specific assumption. Let's assume for the sake of argument that the perturbation I made was a sinusoidal perturbation. You can change this to cosine, you can change this to sine plus cosine, you can do whatever you want. But let us assume that I have actually made a sinusoidal perturbation with some wave number k. Okay. Let us see what happens to this perturbation. Okay, should we do that? Now what happens to the, of course, now B0 is the amplitude that I have initially given. Of course, when over time this B0 will change, right? So B0 will become time dependent. Okay, so left hand side will be now dou B by dou T will be equal to dB0 by dt times sine of kx. There's anyway no time term here, right? So left hand side will be this. Is that fine with everyone? What about the right hand side? That should be equal to lambda times B. So lambda B0 sine of kx. Okay. And then we have this term. What is that term? Plus d times second derivative of the function. So what is second derivative of the function? Okay. So remember, this depends on t. Second derivative of this is what? In x. So derivative of sine is minus cosine, and again it's back to sine. So you have B0 minus k square sine of x. Okay. So let me just write this down. You can see that basically this term is equal to this plus this. Okay. So there's something common across all of them. What is that? Let's assume k is not 0. What's the point otherwise, right? No. Let's assume k is not 0. I can cancel all of them. So I have d b0 by dt is equal to lambda b0 minus k square b0. Okay. So this would be lambda minus k square d and b0. So basically what this means is that I now made a sinusoidal perturbation with some amplitude b0. So this equation tells me how is that amplitude changing over time. So how is it going changing over time? Let's consider two scenarios. There are two possibilities. Lambda is positive. Lambda, this is a simpler case. Lambda negative, meaning the mean field. We're dealing with a mean field stable equilibrium or a fixed point. If lambda is negative, this entire term will be also negative. So therefore, you can call this as lambda k. Okay, so you have db0 by dt lambda k of b0. So if lambda is negative, then lambda k0 is also negative. So lambda k is negative, therefore b0 goes to 0 with time. That means the perturbation that I have made, a sinusoidal perturbation that I have made, actually decays. The amplitude of that decays exponentially with time. From this, what can you conclude now? And this is true for all k values, right? All non-zero cases, all k values. Any sinusoidal perturbation I make will die. If I change this with cos, does it make a difference to the calculations? No, nothing. In fact, the exact same steps will happen. Would be true for cosine as well. And then for all values of k, again, this is true. So if with these, what can I conclude? And remember that, Fourier theorem. Any function can be represented as a summation of sines and cosines. Okay, so even if my perturbed function bx was something much more complex, I could have written them as summation of various sines and cosines, but each of them exponentially dies off. So therefore, what can I conclude from this? The homogeneous V star is if the mean field B star was stable. Any questions on the analysis? Oh, yeah, yes, why not? But you see, okay, you should remember one thing. In a population dynamical system, even a closed system has birth and death. So the numbers can change. It's a diffusion term that cannot change numbers, but the reaction term does change numbers because of birth. Any other questions? Okay. So what we have shown so far is that is the following, right? You remember for the harvesting model, we had this bifurcation diagram, right? It's increasing HR, reducing R. We had this bifurcation diagram, okay? So we determined the stability of this only based on the criteria of lambda, which is F prime beta star, right? Okay, so I should now call it beta star. Now, what about if I now have diffusion on top of the harvesting model, how would this now look like? Will this change? Does it change or not change? No, it should not, right? Because what we have just learned is if you have a mean field stable branch, the diffusion does not change it. Okay, so this will hold true even for harvesting model with so at least there, of course, there are some caveats here. Okay, that one must be slightly careful. Of course, the main caveat follows from the analysis we have done, which is that I'm making a small enough perturbations, therefore I can ignore these higher order terms. Okay, just like in the case of linear stability analysis, right? What if I had made a large enough perturbation here? That wouldn't be true, right? So all this is true even for the small perturbations in the spatial sense now. Okay, one thing interesting you can show is the following. So which I will not be in a position to derive. It requires slightly more involved mathematics, more algebra really, not really mathematics. Is the following. There is a notion of what is called a patch size. Okay, so now imagine there was no space. What would you, if you were here, how can you, without reaching here, how can you undergo a transition? If you are here, you make a massive perturbation to this side and you can jump across, right? So what would be an equivalent in the spatial system? One possibility is that everywhere in space, I push down, in this case, push down everywhere in space to this side, and then that will then cross over. That obviously will work, right? But this actually turns out it actually is easier to switch in a spatial system. Okay, so what happens in spatial system is the following. Okay, this is the spatial system. I don't have to homogeneously cross everybody here. I have to only make a, imagine this entire state is in the, B higher branch, larger value of B. But if I make a hole here with other branch, it turns out that I don't have to make every part of space at this lower branch. I just have to have a critical radius RC, okay, and if I exceed that path, which is called the critical path size, if you exceed that, you can actually switch over, okay. And this, if you can actually show that this RC depends, can you make a guess how will RC change as a function of this parameter H? Let's say you are on the upper branch. Let's say, if you're somewhere here, can you make any RC that can flip over? No. So here it's impossible, right? Whatever large you make, it'll always come back. How about here? There is in principle now possible, right? Okay. But here you can make a guess that this has to be really massive to be able to come back. But what you can show is that in this region, let's call this H1 and H2. It goes like this. Okay. So the closer you are to the bifurcation point, the smaller that critical path size. In fact, it actually hits 0 the moment you actually come to H2. It's something like, I don't know the exact form, is that it's concave or convex. I just done a qualitative functional form, and which means that, of course, this would be true even in the opposite direction. Right? If I am in this state, to go to the other state, it would be again exactly true. And this actually has some interesting application, potential application, right? Imagine you are in a low population state. To reach this one, you don't have to make every part of your landscape better. If you make some parts of it sustain high enough population, which exceeds the critical size, it can actually flip over to other side. Okay. Now this is an insight. This insight about critical path size you can get only from solving a spatial model, something you cannot get from a mean field approaches alone, because that fully ignores how the spatial spread matters. Any questions so far? Critical path size. Now that still leaves us one. So what we are trying to do is, are there which concepts that we have learned from mean field models can be borrowed, right? The stability and fixed point can be borrowed, right? That's fine. But there's a new concept that's not there at all. There is no analog of this at all in the in the non-spatial model. That idea of critical path size, that's a new concept. What's the concept that we would like to investigate more now? Any other thing that you have learned from the time series work in the last 2 days? Huh? Early warning signal. Okay, so you can now ask the question, what about early warning signals? Does spatial organization provide any interesting insights on the early warning signal? Okay. Any guesses? We have already done the necessary mathematics on the board. Okay. Okay. But how does it connect to the early warning signal idea? You are saying you're going to study one area, one small area, and that would be applicable. Okay, okay, that's fine. Okay, that's a good question. What do others think? I can say, if it's a homogeneous space, let us say, that means the conditions are roughly same everywhere. I can study it one location. Why do you need to study everywhere? That's her point. What do others think? But to do that, we need to first show that the early warning signals will work in a space when you have included the diffusion as a term. No, that's one thing that's still missing. Okay, but after that we can ask this question. Okay, then what was the point that? Exactly. So maybe there's something in the way things are spread and that spatial dynamic, something about them that suggests that could actually offer new warning signals also potentially, right? Okay. But does the same early warning signal even work? So what was the previous sort of principle behind the early warning signal? The idea was that if you have again let's look at the mean feed system. So if we have, if we had an equation like this, the idea was that the perturbation follows this equation, right? And the basic idea was that if there is some driver, and if we plot the, this eigenvalue or just the derivative of f as a function of time. This has, of course, at a time, this has the units of 1/time. So it's a measure, it's basically a measure of rate, right? This rate as a function of, it basically tells you how the perturbation decays or grows, right? It's a rate of measurement of how perturbations grows or decays. What we found was that if we now plot it for a stable branch, it would, or how would lambda behave like? First of all, it will be a negative value, okay, right? So because if it's a stable branch, and how will it behave for this branch as I approach this point? So it will be negative, it's 0 at critical value, right? So basically the fact that lambda goes to 0 means that the decay becomes slower and slower. That was the basic idea. That's the idea of critical slowing down. As you approach the bifurcation point, this is what happens. So what's the equivalent? Do we have an equivalent for that with diffusion now? So again, think of the final equation we have derived, how the amplitude of the perturbation is changing. So what was that? That actually had this behavior dB0 by dt, where B0 is the amplitude of the sinusoidal perturbation, grows as lambda k, right, times B0. Okay. And how does lambda k now behave with H? Lambda k has two terms. Lambda k has lambda minus k square d. Let us fix k for the time being. Okay. So that has no effect. So how will that now look like? Lambda minus k squared as a function of H. Given this, some negative value, it again comes. What's the minimum value it can take now? Minus k square d, right? Okay. Yeah. So yeah. And then whatever. So as you approach bifurcation point, the return rate again is reducing. But it's technically not becoming 0 because of the k square term. But now that means does it now have a critical slowing down? Critical slowing down necessarily means that has to hit 0 by the way. So here it is actually hitting 0. But that's not hitting 0 in this case. So does it have a critical slowing down? Not in the sense of this, for this perturbation. Now if you now make an arbitrary perturbation, I know that arbitrary perturbation will have various values of k's, right? It will have k values ranging across the entire possible spectrum. it would even have some amplitude for k is equal to 0. Okay, and but that amplitude, that specific amplitude will show critical slowing down. Okay, and in fact that k is equal to 0 is basically nothing but the homogeneous solution. Okay, so so we do observe two things even in the spatial systems. One is that we do show the return rate reduces as you approach the critical point for all modes of perturbation. But if you make a random perturbation in space, then you will have a k is equal to 0 mode, or some mode will be maximally growing, and that will come sufficiently close to 0, or it could even hit 0. And that mode will actually show critical slowing down, but not every perturbation mode. Okay. So, and the moment that happens, see that now remember that, this equation looks basically, you can add some noise to this. This will look like the Ornstein-Uhlenbeck process or the Langevin equation we have already studied. So all the formulas we have learned there can be applied, but for each spatial, perturbation mode separately. So I hope you understand the idea of modes here. So the idea of Fourier modes is that if I have some spatial perturbation, I can decompose it into many different periodic modes. Okay, so one of them could be sine of some frequency, and that has some amplitude. Another would be another sine of something, another amplitude. So they're all different amplitudes. I am sort of decomposed into linear combination of all this, and each of those modes have slightly different rates of decay. And the slowest one will be the what we actually end up observing, because everything else decays very fast, but the slowest one is what we'll actually observe. Okay, and that will show something close to critical slowing down. Okay. So this suggests that whatever we learned for the time series will also be true for the spatial dynamics in terms of time. But is there any questions beyond this or up to this point? I have shown for one, but if you do Fourier transform, I wanted to avoid all the Fourier integrals. How do you now calculate in real data? Is that your question? That's a great question. Yeah. So his question is, okay, I'm showing everything in the Fourier space, but what I'm measuring is in real space. I mean, I'm just really doing measurements in. So how do I really see it? That's your question, no? Yeah. Okay. So the answer to that question is you have to do you can actually there are mathematical steps involved that you can show that you can now do an inverse Fourier transform and calculate what happens in real space, and that's there in one of my papers long back. But basically, we can conclude, after that procedure, we can conclude two things, 2 or 3 things actually. Okay. What is very interesting is the following. Although we have been talking about things in time, each mode, the amplitude of each mode in time is what we are talking, right? How is that changing? That's all we are saying so far. But if you do some additional math, what you can say is the following. You can actually look at the entire space of, every one of the points will have some value of B, right? And in all the analysis I have shown so far, there is no stochasticity. But of course, in real system, there is stochasticity, okay? And then if you basically include a noise term right here, that just carries forward throughout, okay? What you can show is the following. Because of stochasticity, not every value in space, not every value of population space will be same. It's because there will be variation of the population size from one point to another point. So one thing we can do, as somebody in the back said, was measure only one location that will show all the signatures of critical slowing down, but slightly damped. because of that minus k squared d term. It's damped critical student. That's something you will see. But imagine I'll measure everywhere. Will all of the values be same? They will not be same. Okay. So in fact, what we find is that you can measure spatial fluctuations of population size. This actually increases as you approach tipping point. Remember that everything we have done is actually in time. Okay, but what we can show mathematically is that that has an impact on how spatial organization happens. I haven't shown this mathematically in this class because that becomes another heavy algebraic exercise. I can give you references for those interested, but it's easy to visualize why this is true. Let's say in this location, system is, has perturbations, it is recovering from perturbations. As we are approaching tipping point, the recovery here is slow. Recovery here is also slow. But the randomness here and here is also different, right? Okay, now because the recovery is slow, the deviation between these two also increases. I mean, not necessarily very close by the way, that's a bit tricky. Actually, deviation across space also increases because everyone is now slowly responding. So therefore, not only in time fluctuations will increase, but even in space, spatial fluctuations will increase. And what is counterintuitive and a bit puzzling is that, again, recall what happened, what Partha presented in his presentation. He showed that the autocorrelation in time, that also increases as you approach tipping point. So analogously, what we find is the spatial correlation increases as you approach the tipping point. Okay. So whatever was happening in time, that actually translates to space. What do you think is the statistical advantage of this? Earlier, you had only one measurement of the entire population. And to calculate variance, you needed some long time series. Now, because you are measuring in space, that entire long, whatever 100 year can be substituted by 100 time points in space. So it adds extraordinary power to your calculate metrics in a statistically much more reliable way. Okay, so you often need, so in a time series, imagine you have data over time. To measure whether variance has increased, you need a window of time, and another window of time, and then compare the two, right? So what do you need here? I just need 2 snapshots. Just 2 time points are sufficient to compare whether fluctuations are increasing. So there you needed 2 windows to compare whether correlation is increasing. Here you just need 2 snapshots to compare whether correlation is increasing. Okay. Which is, if you assume that driver and time are correlated, then at each time point I need 1 snapshot. It is not that I'm reducing the number of data points. I'm using the fact that there is space. I'm reducing the window of time where I need to calculate. Okay. Exactly. If around some arbitrary, around the mean value. For example, you can measure this, you know what is variance, right? You can measure spatial variance. Yeah. I'm not assuming. I just showed. Huh? Oh, each spatial. Okay. That I agree. Yes. That's true. Yes, f of b is same for all the points in space. Now, if I add, it's a very tiny amount of equilibrium. Not very strong. Okay. A tiny amount of equilibrium. So this idea, I guess, I think tiny amounts should not change. I would think so. Yeah. In fact, it may even get amplified because the heterogeneity can amplify the signals a bit. I think it's possible that it can even amplify.
I can see them something like stochastic resolution.
Possibly in space now. Yeah. People have shown that the spatial heterogeneities can cause many new types of dynamics also. But one can do something like a frozen heterogeneity, right? But slightly, for example, if the parameter R is slightly varying across entire space, how will that influence? I think, it will be interesting to study. I don't know if anybody has.
Following some distribution?
Exactly. Yeah. Exactly. And that is realistic also, right? Very realistic also. Yeah. And also one can do something called a pinned heterogeneity. There is one place, like, in an island, there's a rock in the middle. So now that's but everywhere else, imagine it's same. So now that's one place has a huge heterogeneity, but everything else is same. One can also study those kind of, I think there are some papers that study this. Physicists study this a lot actually, in the context of, again, phase transitions and how when you move from one phase to other phase, there are these events called nucleation events. How these nucleation events are affected by heterogeneity in the materials. I mean, for material science, doing real materials, some of these problems are actually really important. How heterogeneity change the properties of matter. And there is a phenomenon called pinning there. These heterogeneities act as, they sort of hold on to some values, and it does sometimes can sort of hold the phase transitions for some. I don't know. I'm not an expert, and I have it only very, very vaguely. It can have interesting effects. Yeah. And H. Basically k is equal to 0 is when you will actually find that. But what you need to remember is that what we see is not any individual k. We see that some defect of all k's. Because inverse Fourier transform has summation of all of them, right? So it's only a mathematical trick to understand how to decompose the problem into a solvable problem. But the real world problem will have summation of all of them. That's what we will observe. Okay. And we can, it's the inference is fairly straightforward and clear, right? Because for each k the results are valid, and because what you are seeing is a linear superposition of all of them, the results will be still true for the real data. Yes, I mean, yes, of course, yes. Critical, as I said, this can be analytically derived. In fact, one of my students has a paper to show that along with real data also, this can explain the existence of forest savanna coexistence in African ecosystems. So we'll take a break now. Is that fine? Yeah, we'll come back by 11:30. We can continue to discuss and chat there also.